Alright, today we're going to talk about the information that we need to know of in Chapter 9, but first of all I want to back up to molecular geometry for just a second. This concept map is on the back of the geometry handout that you have, and what I want to point out is that these categories right here are what we refer to, this first group is what we refer to as parent geometries. And I'll explain this in class a little bit more, but this is just electron groups, which are either bonding or electron pairs. So if there's three electron groups coming off of there, the parent geometry is what's called trigonal planar. If all three are bonding groups, you get the trigonal planar. Then the smaller groups down here are the actual shapes or the actual molecule geometries. That's what these are. These are the specifics. So for example, 3 bonds would be trigonal planar. If you had 1 lone pair and 2 bonds, that's this type of bend. You're just going to hear me use that in this slide, or this presentation, so that's what I want you to just make clear. Okay, now with hybridization, again, it said you may want to read this just because it's different. Okay, now we're going to start by explaining that there are some problems if we really look at the bonding in something like methane. All right, if we keep things separate, the bonding between the valence orbitals should be varied. I'm going to draw this out here in just a second, but there'd be one type for the 1s for hydrogen, and for the 2s from carbon, and one type for the 1s from hydrogen and the 2p's from carbon. And what we do know is that all of the bonds are equal, and we know this because we can study bond energies. When we study the bond energies, the carbon-hydrogen bonds that we have in methane are all equal, so we know that something's got to be the same. So the 2p orbitals are perpendicular, but the carbon-hydrogen bonds are all 109.5 angles. Now, there's another slide here, but if we just look at the electron configurations for a second, we know that hydrogen is in the 1s. And if we just look at carbon's valence electrons, what we get is we have the 2s that's filled, and then for the 2p, we have these two. Okay, so these would be carbon's valence electrons, and that's kind of what we are dealing with in terms of how these need to combine, because we know the S's are spherical and we know the P's are dumbbells. So just hold on and see what you can process in the next 15 minutes or so. Okay, so if I get rid of all my ink here come the shapes. So I have that spherical S and the 3 dumbbell shaped, but we know that somehow they all fuse together and we get these 3 equal bonds that are all 109.5 degrees away from each other. Now, one thing that you're going to see in kind of taking things to the next level is that we also will draw these bonds, and if we use a filled in triangle, that usually means that things are coming towards us. And if we use this dotted, like not filled in, that means that it's going away, and then we might have a straight line one. And this is just to show, excuse me, kind of the 3D version, that it's not all in this 2D plane and they're not 90 degrees away from each other. Okay, so what has to happen is what's called this hybridization, that carbon must accept a new set of orbitals used for bonding other than its 2p and its 2s. All 4 have to be the same because it's a type of tetrahedral. And this is where we haven't been telling you all the truth, is that what actually happens is they get these hybrid orbitals, which are these mixing of normal orbitals to form these special bonding orbitals. We get 4 new sp3. Now what I want you to do is recognize the fact that if we think of this as a 1 plus 3 is equal to 4. You're going to see a pattern here as we go through these hybrids. So for the 1, 2s, and the 3 2p orbitals that are utilized in carbon, we end up with this new hybrid shape. And it looks like this giant lobe, one large lobe and one small lobe. But when we need a set of tetrahedrally arranged, we end up with 4 sp3 orbitals. And what it looks like from a bonding perspective is this. You get this, they kind of fill in and they're all equidistant away from each other. So the 1s and the 2p come together to form these 4 sp3 hybrid orbitals. All right, and then the other piece, just so you can see this this way is that if here is the P, here's the P's right here. This is our hybrid, where we have this sp3 that's come together. Here is the hydrogen, here is the carbon. So the hybridization has happened for the bonds that carbon is utilizing. It's taken its S and its P's and it's kind of hybridized them into something different, and they all have a bond angle of 109.5. Okay, now sp2 comes along. If you look at this central carbon, there are 3 bonding groups coming off of either of these central carbons. And so we don't need 4 new orbitals, we need 3 new orbitals. And when we need 3 new orbitals, we get what's called sp2 hybridization. And that's created from the 1 2s and 2 of the 2p orbitals that are being utilized. Same similar shape. They have a trigonal planar arrangement, so the bond angle doesn't change. This is still this 120-degree bond angle, but again, you'll notice if we think of this as 1 plus 2 is equal to 3. So whenever we need a trigonal planar geometry and 3 of them need to be formed, we get this sp2 organization. So we still have a 2p that's not hybridized, but we need 3 of them, so we make 3 sp2 hybrid orbitals. Where's my arrow? There we go. Okay, so what does that look like? Well, again, here is that carbon. Here's one sp2, here's another sp2, here's another sp2, that all form. But what we also have is what happens to the other 2p orbital that did not get included in the hybridization, or that gets left out. Well, it shares an electron pair. And so what you have is above the carbon, okay, you've got a p orbital here and a p orbital here, and they share this electron pair between them. And we're going to separate things. It occupies the space above and below the sharing between the sp2 orbitals. Forms what's called a pi bond. So when you have this kind of overlap of side by side, parallel p orbitals, we make what's called a pi bond. And we're going to look at some molecules and identify how many are there. Now the sp2 orbitals are used to also share electrons, and when you have kind of a hybrid where you have a direct line between 2 atoms, this is what's called a sigma bond. Okay, so sideways overlap is a pi bond, head-on overlap is a sigma bond. Okay, and we have to count these, and we'll do some of these as well. Oops. So on this one, here is the pi bond right here. Here is your sigma bond right here. Here's also another sigma, just because they're head-on. Okay, sigma and sigma. So we've got 4 sigmas on this one. And then the pi's only come in pairs. Even though there's a top and a bottom, this only counts as 1 pi bond. Sorry, 5 sigmas. 1, 2, 3, 4, 5. And I think this next slide is going to show you the same thing. All right, so here is, the sigma bonds between the carbons and the hydrogen, the sigma bond between the carbons, the sigma bonds between the hydrogens, and you have 1 pi superimposed, which kind of ends up overlapping. I know, I'm sorry, it's heady. But every double bond that you have is always going to have 1 pi and 1 sigma. And that's just the way it is. Okay, and each single bond will always consist of 1 sigma. So you still can go back to your regular Lewis structure and come back to this. A double bond is going to have 1 pi and 1 sigma. A single bond is going to have 1 sigma. Okay, so there are some rules to that stuff. Now, whenever we have 2 bonding groups, we only need to have 2 new hybrid orbitals. So it's just going to be 1s and 1p. And they still have this same shape, and it's 180. So whenever it's just linear, which means only 2 groups, we only need the 1s and 1p to hybridize. So what we end up with is we take one of the p's and the s, and we hybridize it into 2 s and p new sp orbitals, and we still have the other p orbitals floating around. So here is the sp right here. Now we got to look at it a little bit different, because these carbons are both going to be sp. Oxygen needs to do sp2 because it's also going to have in order to react with all three of its p sections. So if we look at carbon dioxide, the other two 2p orbitals left out, oh man, okay, are going to create some of these pi bonds that we saw before. They're going to share electron pairs with the one extra 2p orbital from the oxygen. All right, so if we look at carbon, here are the sp ones that are going to share. Here's the extra p's that's just going to have lone pairs floating around, and then each oxygen also has a one to share. So you're going to get a pi bond with the one oxygen, and then remember you've got another oxygen out to the side because it's carbon dioxide. So if we look at it, we've got a sigma bond right here because it's head on, okay, and it is a even though it's double bond, we only get one sigma for head on, and then we get two pi bonds, one here between this carbon and this oxygen, and one over here between this carbon and this hydrogen. So when we have, again, with our double bonds, since we have two double bonds, we have one pi bond and one sigma on one side and one pi bond and one sigma. So it still follows that rule that we already had. Okay, I'm going to keep going because you're either catching on at this point and it's making sense, or you have no clue and you're going to hear me have to explain it again. So I'm just going to try to get through these and get through the rest of the slide here. If we have PCl5, we've got 5 bonds that need to be generated. So what we're going to do is we're going to have the sp3, and we're also going to add in one of those D's, which if we have a 1 and a 1, that equals 5 orbitals to combine. So we've got one 3s, three 3p's, and one 3d that are going to make these new sp3d orbitals. They've got the trigonal bipyramidal relationship. But in essence, what we do is we take them, we blend them, and we get 5 equal bonds is really what it's doing. And so again, with SF6, we need 6 of them, and we're going to draw some of these on our geometry chart, and you'll see that there are some patterns. So if we need 6 of them, we're going to have an S, we're going to have 3 P's, we're going to have 2 D's. That's going to get us to a total of 6, which gives us octahedral. Or in other words, when we need 6 equal bonds, we get, and sometimes you'll see it rearranged this way, to D2sp3, but two Ds, 1 S, and 3 Ps. Now there's a nice little chart on page 424. Again, we're going to do some more of this in class and go over it again because it is new and it is heady. But process-wise, if you think about this, it would start at the very beginning where you draw the Lewis structure, you determine the arrangement of the electron pairs, you identify the geometry, you identify the hybrid orbitals. It's just several sets of questions based on starting at the beginning. You also could identify the bond energy, etc., etc. Okay, so if we look at a few of these, if we have ammonia, it wants you to describe the bonding. So the parent geometry is tetrahedral because there's 4 groups coming off of that central nitrogen. Now 3 of them happen to be bonding, 1 lone pair, so the specific geometry is going to be trigonal pyramidal. We could identify the bond, and since we have 3 or 4 bonding groups that need to come off of that middle, what we end up with for hybridization is going to be sp3. Okay, so, and we'll get a sigma bond between all the head-ons. We don't have any pi bonds because we don't have any double or triple bonds here, but it's going to be sp3 hybridization, and we still end up with just a lone pair in that 4th hybrid section. Okay, so like I said, 3 sigma bonds and no pi bonds for this one. Another example would be to describe the bonding in diatomic nitrogen using the localized electron model. Here you have 2 nitrogens that have to face, and so what we're going to end up with is an sp overlap because we need 2 orbitals in order to make this work. And since it's a triple bond, what we're going to end up with is 1 sigma bond with them facing head-on because we just need 2 orbitals to overlap, but we also end up with 2 pi bonds. So just like we saw with the double bond, when it's 1 sigma and 1 pi bond, anytime you have a triple bond, it's going to end up being 1 sigma and 2 pi bonds because there's 2 extra empty p orbitals that are available to share electrons. And that's what that's showing you right here with those green lines. Okay, if we've got, and this is getting up there, but just to show you, if we look at the